This is a lesson on black body radiation and quanta. So we've explored black body radiation when we looked at continuous spectra in this module, near the very start of this module, and also in Year 11 physics, briefly, when we did thermodynamics in module 3. So if you recall, a black body is an object that absorbs all radiation that falls on it, incident on it, but it doesn't reflect any radiation. So it's a perfect absorber of EM radiation, electromagnetic radiation. Now, radiation that's emitted from a black body at different temperatures gives you these different curves as follows. Okay, so let's plot wavelength on the x-axis and intensity on the y-axis. Okay, let's stick with arbitrary units. Suppose get these different plots as follows. Okay, the peak of these curves, of each of these curves, corresponds to the maximum wavelength of radiation. So the total radiation emitted is the area under the curve, under each curve, right? And when the temperature of the black body is increased, you get more intensity, right? This makes sense from everyday intuition. You increase the temperature of, suppose you have a light bulb, you can increase the temperature as much as you want. The higher the temperature, the more it glows and the more intensity, right? And the more it sort of irritates your eyes. So you'll notice here with these curves, the first curve here at the top has the greatest intensity, corresponds to the greatest intensity, right? In other words, a greater temperature, because wavelength drops as you go across the left of this graph, okay? And if you decrease the wavelength, okay, if you shorten a wave, as opposed to the bottom wave here, you get more energy and hence more temperature. Okay, the higher the temperature, the greater the energy, and the shorter the wavelength. Okay, and that's what these series of curves are showing, okay, for illustrative purposes. The second and third graphs are less intense because they correspond to a greater wavelength, okay, such as wavelengths shown here and here. Let's suppose the first curve corresponds to this wavelength, second one this one, and the third one this one. Now we can quantitatively relate the wavelength of light, of EM radiation, with that of the temperature of the radiation through what's known as Wien's law. If you recall, Wien's law simply states that the maximum wavelength is related to the temperature, is inversely related to the temperature through a number constant known as the Wien's displacement constant, which is 2.898 times 10 to the minus 3 meter Kelvin. Meter Kelvin because wavelength is measured in meters, temperature is measured in Kelvin. If you rearrange this formula, B is equal to lambda sub max T, you get meter Kelvin. And this is on the HSC formula sheet. Okay, Wien's law and the Wien's displacement constant. Okay, so lambda sub max is the wavelength where the emitted light intensity is the greatest, as I mentioned before. And T is what's known as the absolute temperature of the body's surface. Absolute meaning the real temperature. This is really powerful because you can determine the wavelength at which the most intense black body radiation is emitted from an object like a star. And if you know the wavelength, you can then work out the temperature of the star, and then you can work out other things like its density, what it's made of, what elements it's made of, etc., how fast it's moving, how fast it's rotating. So it's very, very powerful. And in astrophysics, they have a saying, if you know wavelength, you know everything else. That's what I was told, at least, by a colleague. Now, around the late 19th century, there were attempts to theoretically explain black body radiation. The black body radiation curves shown up here, okay, using classical electromagnetic theory. So the theory of Maxwell. And it was shown to fail. Okay, it basically predicted that the radiation emitted at high frequency should be much more intense than the radiation emitted at low frequencies, okay? And you would see this sort of divergence at high energies. So let me just graph it quickly. Suppose you have intensity on the y-axis as before, and you've got wavelength on the x-axis, and you've got this black body radiation curve. Now, according to classical electromagnetic theory, using Maxwell's idea of waves, this is what would happen. So at long wavelengths, there was agreement. Okay, low energies, there was a bit of agreement with the experimentally measured black body radiation curves. However, as you go towards the UV part of the spectrum around here, the graph starts to diverge. Diverge means to move away from the actual data given by this highlighted curve. And this is known as the ultraviolet catastrophe, the UV catastrophe. And this came from the Rayleigh-Jeans law. Okay, two British physicists came up with a law known as the Rayleigh-Jeans law. And they used classical physics, classical electromagnetic theory, and they found that it failed at high energies, but it agreed at low energies. Now, 1896, I should say the Rayleigh-Jeans law was developed around 1900. Just before that, 4 years before that, 1896, Wien, so the German physicist Wilhelm Wien, the same guy from Wien's law up here, he proposed a theory, a model, just like Rayleigh-Jeans, but it turns out that it actually worked at high frequencies and it failed at low frequencies. So the exact opposite of the Rayleigh-Jeans law. The Rayleigh-Jeans law works at long wavelengths, right? Low frequency. The Wien displacement law worked at short wavelengths and high frequencies. So I'll draw on the same graph. The Wien's law works as follows. So in red, it's overlapping the blue, and then it sort of diverged from that at lower energies. Then this brilliant guy named Max Planck, German physicist, who is known as the father of quantum mechanics, kickstarted quantum physics in the 20th century. Max Planck, in around 1900, okay, about the same time as Rayleigh-Jeans, he worked backwards. He had this brilliant insight. He worked backwards from the answer to see what assumptions he'd have to make to derive the mathematical model, the equation, from known physical principles. And he called it an act of desperation. So Planck didn't really like the consequences of his theory, but he thought it was basically just a mathematical trick to make the model work, fit the experimental data. And he successfully reproduced the black body radiation curves. And unlike classical physicists who assume that oscillating charges supposed to have an oscillating dipole, plus minus. If you remember, there was nothing known about atoms at the time, the year 1900. So physicists believed there were oscillators making up every material. So oscillators would oscillate, and that oscillation would result in radiation emission, right? And unlike classical physicists who assume that oscillating charges could oscillate with any amount of energy. So according to classical physics, any amount of energy is possible, even infinite amounts. Planck made these two radical assumptions, okay? And the first one was that he proposed that the energy of these oscillators, which we now know to be atoms, the energy of the oscillators was quantized. This is a bit of a big word. Quantized means comes in discrete amounts, in very specific amounts and not just continuous amounts. Think of a string as opposed to a string with beads on it, right? String with beads on it is quantized. It's made of chunks, and the piece of string is continuous, okay? And I was able to show this mathematically. So quantized mathematically means that there's a whole number multiple of a specific minimum amount. Specific minimum amounts of energy. You can only have a specific amount of energy being emitted by the oscillators, and not any amount you want. And this was actually related to This is related to the oscillator frequency. So he found that mathematically he could express the energy of the oscillator with the frequency of radiation emitted, right? So E is equal to HF. It's very simple. I should put an N in front of the H and F. Explain what this is about. E is measured in joules. E is for energy. It's the minimum quanta. So quantum, one quantum of energy is a chunk. Think of it as like a blob. Quanta is plural, more than one, right? So minimum quanta of energy, okay, for the oscillator. H is a number that was derived by, that was actually, it was actually a guess by Planck. Planck guessed this number to be 6.626 times 10 to the 34 minus 34 joules seconds. And this now bears his name. It's called Planck's constant on the HSC formula sheet. It's a number, and it helps equate energy and frequency. And F is just the frequency of the oscillator. Okay, typically in hertz. This was the breakthrough. And N is just a number, a whole number, an integer. So N could be 1, could be 2, but N couldn't be a half or it couldn't be 0.75, okay? So you can't have, N cannot be fraction, okay? N has to be an integer. That's the idea of energy being quantized. Energy comes in specific amounts, specific whole number amounts. You can have HF of energy, you can have 2 HF, 3 HF, but you can't have half a HF. Just doesn't work. That was his first radical assumption. His second radical assumption was that oscillators could only absorb or emit whole number multiples of minimum energy, of minimum quanta. Okay, so in other words, light is only emitted or absorbed by an oscillator in chunks, in little quanta. Okay, so light can be thought of as chunks coming in. Oscillator can only take in 1, 2, 3, etc., but it can't take in half a quantum, right? And Planck didn't like this idea, and he only believed that light being absorbed or emitted, that these particular quanta were like a mathematical trick, okay, to get the correct answer. And he didn't believe that this was actually happening in real life. Now, because energy quanta are so small, physicists often express their energy in terms of electron volts. Okay, electron volt, okay, E with a capital V, small e capital V, rather than joules. So 1 electron volt is basically the energy gained by an electron when it's accelerated through a potential difference of 1 volt. Okay, think of it as like the poles of a battery, plus or minus, pass an electron through. Okay, it gains energy. Okay, because there's work being done on the electron as it's moving by the potential difference, by the electric field. Now let's see how this works. So eventually Planck's work actually led to a completely new realm of physics called quantum physics, quantum mechanics, and it really revolutionized our world. Our world became a lot more digitized, more technological, and it's all thanks to quantum physics. Let's do an example to see how Planck's formula works. So suppose we need to work out the minimum energy in electron volts of an electron oscillating at a frequency of 4 times 10 to the 14 hertz. Okay, so we need to use the formula E equals NHF, Planck's formula. Now, typically in these questions, you can just omit the N, okay, instead of equal to 1, if it doesn't specify. So E equals HF. We know what H is, we know what F is. Let's work out E. So H is simply from the formula sheet, the data sheet, I should say 6.626 times 10 to the minus 34. And the frequency is 4 times 10 to the 14. Plug those into your calculator, you get 2.65 times 10 to the minus 19 joules. Now we're not done yet because the question specifies electron volts. So how do we convert from joules to electron volts? We divide by 1.602 times 10 to the minus 19, which is basically the charge of the electron, right? It's on the formula sheet. And I forgot to mention, the energy gained by the electron passing through the potential difference equals QV, right? Because that's equal to work, if you recall. It's just 1.602 times 10 to the minus 19 times 1, right? 1 volt, and that's the charge of the electron, and you get 1.602 times 10 to the minus 19 joules. That's how many joules there are in 1 electron volt. Okay, that's the conversion factor. So dividing by 1.602 times 10 to the minus 19, we get 1.65 electron volts. And also just a note, since H, Planck's constant, is so small, we don't actually notice these quantum effects in the everyday world, the everyday macroscopic world. Okay, because H is so small, we don't notice these quanta processes happening around us. They're pretty amazing. We can actually calculate things like this. And Planck's work was quite revolutionary, as we'll see soon, in explaining the microscopic quantum world.